This server rack is running at its thermal limit, which has become the standard for modern enterprise AI. We've moved past simple chat interfaces into deep, multi-document reasoning, tasks that require massive, continuously expanding context windows to function. But scaling those context windows has hit a physical barrier called the KV cache bottleneck. It is the point where a model simply runs out of available memory. This happens because the model must convert every processed word into a high-dimensional vector. These vectors are stored in the GPU's VRAM as a reference file known as the key value cache. As the text length grows, this cache expands, quickly filling the GPU's fixed memory capacity. This expansion forces companies into a cycle of constant hardware acquisition just to maintain performance. The resulting capital and operational costs are becoming unsustainable, proving that simply adding more hardware is no longer a viable economic strategy. Some developers have tried token dropping, manually deleting parts of the cache to save space. But when you permanently erase contextual data, the model loses its ability to handle precise tasks, like finding a single specific detail in a 1,000-page contract. Another workaround is scalar quantization, which rounds off numerical values to shrink the file size. This rounding introduces mathematical biases that compound across the neural network, eventually causing the model to lose logic and generate hallucinations. Enterprise leaders are currently stuck between high costs and logical errors. To move forward, the industry has to look for a solution that doesn't rely on physical memory expansion. This graphic shows the results of TurboQuant, a software-based approach developed by Google Research. It allows for a 6-fold reduction in memory usage and an 8-fold increase in performance without losing the model's accuracy. TurboQuant addresses the root of compression waste, the Cartesian coordinate system. Plotting data on standard X, Y, and Z axes creates erratic distributions, requiring extra memory to store quantization constants that track where the data actually sits. Looking at this 3D scatter plot, you can see how clumped the data is. Traditional compression has to record all that irregularity. TurboQuant's first stage, PolarQuant, moves away from this grid in favor of high-dimensional geometry. The algorithm starts by applying a random high-dimensional rotation to the data vectors. By mathematically spinning the data, the points are forced into a uniform, symmetrical distribution. Then, PolarQuant maps this uniform data into a polar coordinate system. Instead of tracking 3 different axes, the data is recorded by its radius and angle, locking the points into fixed circular grids. Because the data is now in a predictable pattern, the system no longer needs to store those extra quantization constants. This removes the metadata overhead, freeing up massive amounts of memory while keeping the core information intact. Even with this geometric restructuring, compressing data to this degree always leaves behind a microscopic amount of residual error. In deep neural networks, these tiny mathematical deviations add up across thousands of layers. If left uncorrected, they eventually lead to logic failures. This is where the second stage comes in, Quantized Johnson-Lindenstrauss, or QJL. It acts as a mathematical safeguard against those compounding errors. Watch the jagged error waveform here. QJL uses a single sign bit to compress the remaining error, outputting only simple +1 or -1 signals. This creates what mathematicians call a zero-bias estimator. This single bit ensures that the overall statistical value of the model's attention scores remains identical to the original high-fidelity data. By ensuring zero statistical bias, QJL prevents structural hallucinations. This allows enterprises to compress their models for efficiency without risking the reliability of the AI's output. This visualization of data pulsing across the globe represents the practical shift this software enables. With lower memory requirements, advanced AI can move out of specialized data centers and onto more distributed local devices. TurboQuant isn't just a clever hack. It operates at the information-theoretic lower bound. In physics and data science, this is the absolute limit of how much a vector can be compressed. Because the approach hits this fundamental mathematical limit, the algorithm will remain efficient even as models scale to much larger parameter counts in the coming years. There is also a major operational benefit for immediate use. The architecture is training-free and plug-and-play. Unlike standard AI updates, companies don't need to spend millions of dollars in compute to retrain their models. TurboQuant can be layered directly onto existing live production environments. Relying on hardware alone to scale AI has become a strategy of diminishing returns. To make these systems commercially viable and truly scalable, the focus must now shift to the mathematics of the software layer.